seminar. So our lecturer today is Michael Giudici from University of Western Australia, and he will talk about the basis for permutation groups and Saxl graphs. So Michael, please.
Okay, I'll just share my screen. Should work. Yep. Okay, so so I want to talk about bases for permutation group and the Saxl graph. So most of the stuff in this talk is what I did. Oh, it says sharing paused. Can you actually see my screen? Still?
Yes.
Yes.
Yeah.
All right. For some reason, my thing says that sharing is paused. There you go. Okay, so bases for permutation groups and the Saxl graph. So most of this is joint work with Tim Burness. So what do I mean by base for a permutation group? So I have a group G, which is a subgroup of sim omega. And
hey, Michael, your slides aren't moving.
My slides aren't moving, so that's probably why it's not sharing. That's,
I think when you went full screen, it didn't go full screen for us.
Right, so if I now share screen, now that it is full screen, then maybe that is good. Is that?
Yeah, that was better.
That's better. And I move?
Yeah.
Thanks. Right. Okay, so I've got a group G, which is a subgroup of sim omega, and it's going to be transitive. I'm only going to deal with finite sets here, and I'm always going to have the size of my set will be equal to n. And then if I have a subset of my set omega, this will be a base for G if the pointwise stabilizer of my subset is 1. Okay, so the only element in my group which fixes omega 1 and fixes omega 2 and fixes omega 3 and so on all the way up to omega k is the identity permutation. Now, this is sort of like meant to, I suppose it's called a base because it generalizes the notion of a basis of a vector space. Because if I take my group G to be the general linear group of an n-dimensional vector space over my field F, then if I take omega to be the set of all the non-zero vectors, then if I have a basis for my vector space, then that's a base for my group G. Okay, because we know that if I have a linear transformation which fixes all the elements of the basis, then since linear transformations extend linearly, then they will fix all the vectors in your vector space. So that's where I suppose the name comes from. Now, in general, though, I suppose the notion of a base is not as good as a basis because you've got things like all bases of a vector space have the same size. That's not true for a base. For example, if I have a base for a permutation group, I can always just throw in an extra point and that's still going to be a base. So bases of permutation groups don't always have the same size, and so they don't always have the same nice properties as the basis of a vector space. But they are very useful, and they were introduced by Sims in the 60s for algorithms in computational group theory, and in particular for computational permutation group theory. Okay, many algorithms for permutation groups, essentially what they do is they first find themselves a base in a strong generating set, and from that the algorithms for calculating things in the permutation group are able to use the base in the strong generating set to do the computations. Now, one reason why they're very useful is that essentially a permutation is uniquely determined by what it does on a base. Okay, so if I have some base for my group G, so omega 1, omega 2, up to omega k, and I have two elements in my group which agree on a base. So that means the image of omega 1 under G1 is the same as under G2. The image of omega 2 under G1 is also the same as under G2, and so on. Well, then if I take G1, G2 inverse, then that's going to fix all my elements in the base, and so it must be the identity permutation, and so G1 is equal to G2. So in some sense, if I want to store my permutations in my group, I only really need to store their images under a base. Okay? And in particular, the order of my group must be at most n to the k. Okay? So because each permutation, I've got the images. If I have an element in my group G, I take the images under the base, and I can only have at most n to the k different possibilities of permutations in my group. Okay? So that's one of the reasons why bases are nice. Well, as I said, the size of the base is not uniquely determined, unlike a basis. And so the bases that we're interested in are those of minimum size. Okay, and so we let B of G is this important parameter that we'll use a lot. And this is the minimum size of a base for your group G. And for a few standard permutation groups, well, for example, if I take the symmetric group Sn, then the minimum size for base is n minus 1. Okay, if I fix n minus 1 points, then I've also got to fix the last point. Okay, but if I fix fewer than n minus 1 points, then there's always room to do some commuting on the remaining points, and so I wouldn't have a base. For an, the minimum base size is n minus 2. So again, now if I fix the first n minus 2 points, I can't just interchange the last 2 points because I need to have an even permutation. So once I fix the first n minus 2 points, I fix the remaining 2 points. And so I have a base size n minus 2. And again, that's best possible. And then I suppose the other thing to note is that I'll only have a base size 1. Well, that means that there's some point which when I fix the stabilizer of that point is the identity permutation. And so since I was assuming that my group G is transitive, that's only going to happen if and only if my group G is regular. Okay, so there are a few sort of like simple cases of base sizes for a group. Now, I wanted to mention, since a lot of you are graph theorists, a common parameter that you would study in graph theory, instead of looking at bases, you would look at the distinguishing number of a group. Okay, and so the distinguishing number, this is usually denoted D of G of a permutation group, is the smallest number of parts in a partition with the property that only the identity permutation fixes every part. Usually some people, I suppose, instead of thinking about a partition of omega, essentially you're coloring the points of omega, right? And so all the points in the same part get the same color, points in different parts get different colors. And so you want to have a permutation. The only permutation which fixes all the color classes is the identity permutation. Then there's been a lot of work looking at distinguishing numbers for graphs. This is where you just take your permutation group G to be the full automorphism group of your graph. And this was introduced by Albertson and Collins in 1996. And this has been, there's been many papers looking at distinguishing numbers for groups and also distinguishing numbers of graphs. Now, how does the distinguishing number relate to the base? Well, the distinguishing number for a permutation group is at most the base size plus 1. So if I take a base B of minimum size, then I could give each element of B a distinct color, and then I color all the remaining points with another color. So now I've got a partition into B of G plus 1 parts. And then if I'm fixing that partition, well, then I must fix each individual element in my base B, and hence I must be the identity permutation. So the distinguishing number is at most base size plus 1. Okay. Now, I want to talk mainly about bases for primitive permutation groups. So remember that a transitive permutation group G on a set omega is primitive if it preserves no non-trivial partitions of your set. Okay, so it's imprimitive if it preserves some non-trivial partition, and it's primitive if it preserves no non-trivial partition. By non-trivial, I just mean my partition has at least 2 parts, and each part has at least 2 elements in it. And then there's this classic result by Bockett in 1889, which says that if G is primitive and on n points, and an is not inside G, then there's a base of size at most n over 2. Now, I suppose if you're a very alert person, you may want to know how could Bockett have done this in the 1880s when bases were only introduced by Sims in the 60s. Well, so yes, he didn't have the term base. He was more interested in calculating a bound on the order of a primitive group, but the arguments that he was giving were essentially he was like constructing a base. And so from his argument, you see that there's a base of size at most n over 2. So a lot of the, I suppose, finding the order of a primitive permutation group was a big problem in permutation group theory for many years, and it's sort of like interrelated a lot with calculating the size of a base. Now, there's been a lot of work in a primitive group case. Now, one particular avenue of research is trying to find an absolute bound, right? So Bockett, his bound is in terms of n, the degree of the set. If we want an absolute bound, then there is a conjecture in that vein. So first of all, we've got to separate out a few actions which there is no absolute bound for the base size. So what we do is we call two different sets of actions what we'll refer to as standard actions. So the first is if I take AM or SM acting on the set of K subsets of 1 up to M, or on the set of all partitions of 1 up to M, then we refer to those as standard actions. And the other standard actions we'll refer to if I take a classical group, so something like an orthogonal group, a unitary group, a symplectic group, and acting on the set of subspaces of a natural vector space, then that's also what's referred to as a standard action. Okay, now these are sort of like very, I was going to say easy to deal with, but perhaps not easy to deal with, but they're sort of like actions which you can really get your handle on because they're very geometric. So a lot of work can be done with those. There has been work involved in trying to calculate the base size in these actions, but typically the base does grow as a function of n. The base size grows as a function of n. But there's a conjecture of Peter Cameron, which he made in 1992, which says that there exists a constant C such that if G is an almost simple group acting primitively in a non-standard action, then your base size is at most C, your minimum base size. And so as long as you're not in one of these sort of like nice standard actions where it's very geometrical and you can work out what's going on, then there should be this absolute constant which bounds the base. Now, at the time, Peter sort of said, well, the largest example I know is M24 acting on 24 points, and that has a base of size 7. Maybe that's the largest constant, but he wasn't really conjecturing that, but he said that there should be some constant. Well, Liebeck and Shalev, 7 years later, they showed that a constant C, such a constant does exist. They didn't work out the constant though, because this is one of these probabilistic group theory proofs where they sort of like show that the probability that they calculate the probability that there is a base of size C. They show that it's non-zero and therefore there must be a base of size C. But it's done without actually revealing what the constant C should actually be. So then, after a lot of work, all involving Tim with various co-authors, they were able to prove that C equals 7 is actually the largest possible, and equalities if and only if G is M24 acting on 24 points. Okay, so somehow Peter his intuition was correct. The largest example he knew was indeed the largest example. Okay, so this is proved over a sequence of 4 papers. The first one, Burness, Saxl, is looking at where the Saxl is an alternating group. The second paper by Tim is then where it's the classical group case. Third paper with Tim, Anna Shalev, and Mark Liebeck is doing the exceptional group case. And then finally, Tim with Eamon O'Brien and Rob Wilson was looking at the sporadic group case. So C equals 7 is this thing. So we do have this nice absolute upper bound on the size of the base for an almost simple group, as long as it's a non-standard action. Now, it turns out actually quite recently, Tim's pushed this a bit further and shown that actually, well, when can I have a base of size 6? Well, actually, there's only 3 infinite families and 4 sporadics. So that's quite nice. Okay, I suppose the 3 infinite families, you could sort of say they're sort of like a standard action because they're actually an exceptional group in a parabolic action, but that's sort of like something else. Okay, so that's for the almost simple groups. Now, I suppose for primitive groups, there's many other sort of primitive actions. There's like affine actions, there's product actions, diagonal actions. So what about a general primitive permutation group? Well, there is this conjecture of Pyber, but the motivation comes from the following observation. Okay, so if I have a base of size B of G, then as I saw before, the order of my group is at most n to the B of G. And so then we have that rearranging, we get log the order of G divided by log n is at most B of G. Okay, and Pyber conjectured that actually that should be roughly what the base size should be. Okay, he says that there's this constant C such that for all primitive groups other than AN or SN, then your B of G is at most C times log order of G on log N. Okay, so you get this nice, this obvious lower bound, and he's essentially saying that really your base size is not really that much bigger. It's only a constant larger. So that was Pyber's conjecture. So this was made actually before Peter Cameron's conjecture in the almost simple case. And in 2018, this was actually proved. And so it was finally proved by Duyan, Halassi, and Marotti in 2018. But I suppose just to say, actually, this hides that there's a huge amount of work done by lots of people going through various cases, right? So there is the Owen-Scott theorem for primitive groups. You've got the almost simple groups, so the non-standard actions, they're done by the Cameron conjecture, but then you still got to do all the standard actions to show that they meet this bound. You've got to also look at affine groups. So this paper essentially looked at the last remaining case, which was the affine group case. There was also lots of work in, say, the other primitive group types like product action type and diagonal type and all that sort of stuff. So these are sort of like the final three people. They still did a lot of work, but I'm just saying there's like also a lot of work behind that. So they're showing then that B of G is at most 45 times log G on log N plus some constant. And then a year later, Halassi, Liebeck, and Marotti, they improved the arguments to get what is the best possible bound, right? That actually really B of G is at most twice log G on log N plus 24, and this is asymptotically best possible. So, and then another thing they're also able to prove is that B of G is at most the maximum of root N and 25. So whereas the bucket bound said that B of G was at most N over 2, actually, I suppose the better, more correct bound is root N. As long as N is large enough, then the correct bound should be root N. So that's essentially what is known for base sizes of primitive groups. Now, one thing though we want to know is, well, what are which groups have a small base? And so Jan Saxl, he proposed program that we should determine all the primitive groups which have a base of size 2. Okay, so these are the primitive groups that have order at most n squared, and so such groups are called base 2 groups. Now, what does having a base of size 2 mean? Well, there's got to be 2 points such that the stabilizer of those 2 points is trivial. So that means there's one point alpha, if I fix alpha, then there's some other point beta for which G alpha beta is trivial, which means that if I take the orbit of beta under G alpha, that will have size the order of G alpha, and so that's going to be a regular orbit. Okay, so there's always a base of size 2, precisely when your point stabilizer has a regular orbit. Now, equally for a transitive group, so G alpha beta is just G alpha intersect G beta, but G beta is just a conjugate of G alpha by some element. Okay, so to have a base of size 2, I just have to find 2 conjugates of the point stabilizer whose intersection is trivial. So that's what it means to have a base of size 2. Now, which primitive groups have a base of size 2? Well, in that Burness, Saxl paper, which proved the Cameron conjecture for groups with an alternating socle, I actually showed as long as M is large enough, if I have a non-standard action of AM with N at least 12, then there is a base of size 2. Okay, so actually most actions of a primitive group with socle AM have a base of size 2. And actually this turns out to be the case, right? It turns out that most primitive groups, okay, except in sort of like standard actions, but a lot of the non-standard actions, a lot of them will have a base of size 2. Well, once you know that there's a base of size 2, the next question is, well, how many bases of size 2 are there, right? Or also, if I take 2 random points, what's the probability that those 2 random points will be a base? Okay, so there's lots of sort of questions that you want to know. Okay, once you know that there is one base, you want to understand which pairs of points actually are bases. And so that's what Tim and I thought we'd look at, trying to understand, if there is a base of size 2, which points give me a base. And so we introduced what we've called the Saxl graph. And so this is a graph. I've got G as a permutation group on a set omega. It's transitive, it has a base of size 2. And then the graph will have vertex set omega, and we'll join 2 points by an edge precisely when that's the base. So it only makes sense to define these for base 2 groups. Okay, if my group does not have a base of size 2, then I'm just getting a graph with no edges, the edgeless graph, or the empty graph, depending on your taste as to what you want to call it. Okay, so we only study these for groups with a base of size 2, okay, or for base 2 groups. Now, we then wanted to study this graph to see what we could say about it, and hopefully, understanding this graph would give us then some understanding for which pairs of points give me a base of size 2. So there's some obvious observations that you can make. First is that, well, when's my Saxl graph going to be complete? Okay, that means that every pair of points is going to have to be a base, okay, which means that the stabiliser of any 2 points has to be trivial. Well, that's precisely the definition of a Frobenius group, right? Permutation group is Frobenius if it's got 2 points such that the stabiliser of any 2 points is trivial. So that's when I get a complete graph. The other obvious observation is that, okay, my group G, it acts on the set omega as a permutation group, and it will map bases to bases, and so therefore my group G is contained in the automorphism group of my Saxl graph. It's vertex transitive because we're assuming G was transitive to begin with, and it's also semi-regular on arcs, okay, because the stabiliser of an arc is the stabiliser of the 2 vertices alpha and beta, such that alpha and beta form a base, and we know that's trivial. Okay, so I've got this vertex transitive graph. The other observation is we can calculate the valency fairly easily, and that is going to be that, well, if I have my vertex alpha, what are the points adjacent to it? Okay, they're the points beta which form a base, and so they're the points beta which lie in a regular orbit of G alpha, and so each regular orbit has size the order of the vertex stabiliser, and if R is the number of those regular orbits, then R times the order of G alpha is going to be the valency of my graph. So if we know the number of regular orbits and we know the order of G alpha, we can calculate the valency. So there's some like simple observations you can make about this graph. The next thing, well, let's look at a few examples, right? Let's see what graphs we actually get. Okay, so let's work through a few different permutation groups. So going back to my first example of a base, if I take GL2Q, I take omega to be all the points in my vector space except the 0 vector. Then again, we see that UV is a base, if and only if it's a basis of my vector space. And so then what is my Saxl graph? Well, it's going to be the complete multipartite graph with Q plus 1 parts of size Q take 1. Okay, so if I have a vector, then it's going to form a base with every other vector which is not a scalar multiple of it. Okay, so there's Q take 1 scalar multiples of it, and all the rest of them are going to form a base for me. Okay, and so there's Q plus 1 one-dimensional subspaces of this vector space. So I'm going to get Q plus 1 parts of size Q minus 1, and it's a complete multipartite graph. Okay, so I can get complete multipartite graphs from this construction. Next, if I take another example, let's take PGL2Q now, and usually that acts on the Q plus 1 one-dimensional subspaces of my 2-dimensional vector space. But instead of looking at that action, I want to look at the set of unordered pairs of one-dimensional subspaces of my vector space. Okay, and so for this action, the stabilizer point is a dihedral group of order 2 times Q minus 1. And then you can show that if I take two subsets, then they form a base, if and only if their intersection has size 1. And okay, we all know then that that's graph then is the Johnson graph. Okay, so I get these nice Johnson graphs. They're arising as the Saxl graph, the PGL2Q. Next, another familiar example. Okay. I'll take omega now to be a field of order q squared. I'll take an element of order q plus 1 on 2. Then I can have two permutations of omega. One is multiplication by my element xi. One is the q power map. Then the group of permutations generated by xi hat and sigma. That gives me a dihedral group of order q plus 1. If I then take the group of my field under addition, and I take V semi-direct H, okay, H is giving me an automorphism group of this group here, so I can form my semi-direct product. Then it turns out in this group, two elements give me a base, if and only if their difference is a non-square. And so here my Saxl graph is the complement of the Paley graph, P of q squared. But we know, of course, that the complement of the Paley graph is isomorphic to the Paley graph itself. So we're getting here the Saxl graph is the Paley graph. Okay, so we're getting these nice graphs arising. So we're getting the Paley graph and Johnson graphs. Perhaps at this point, I should say, you may ask, well, does this mean that the Saxl graph is a strongly irregular graph? Because the examples I've given you are strongly irregular graphs, but no, I've led you down the wrong path. They don't have to be strongly irregular. Okay, so the first thing we thought we'd look at was, well, can we look at groups where the Saxl graph has prime valency? And then it turns out we had a nice characterization of this. Okay, so if I have a group and the Saxl graph has prime valency, then it turns out only three possibilities can happen. We can either get a complete bipartite graph on 2p points, we can get a complete graph on 3 points, or we can get a complete graph on p plus 1 points where p is a Mersenne prime. Okay, so prime valency is quite restrictive. I'll say a little bit about the proof. It's not, I suppose, too surprising because we saw that the valency of a graph must be the order of your vertex stabilizer times the number of regular orbits. And so if the valency is a prime, that tells you your point stabilizer must have a prime order, and it can only have one regular orbit, which means that the rest of the set are fixed by your point stabilizer. So you've got like p points being your orbit of your point stabilizer, but all the rest are fixed points. But your fixed points of the point stabilizer, they give you a system of imprimitivity. So the number of fixed points must divide the size of the set you're acting on, which tells you you've either got p plus 1 points, which means a set of size p plus 1 fixed point, or you must have 2p points. So you've got an orbit of size p and p fixed points. So that's what happens in this case. And here is where you have an orbit of size p and 1 fixed point. So that's what happens. That's how these ones appear. So that's what happens with the prime valency. Another thing you might want to look at is connectivity. So, and we showed that, well, if I had any odd prime, then there is a imprimitive group G with a base of size 2, and for which the Saxl graph has exactly p connected components. So you can sort of get arbitrarily large number of connected components. I was looking at this today, and we actually don't have a construction which tells you you can have n connected components for any integer n. Okay, our construction, we're using X with special groups, and so we're only getting a prime number of connected components. So that's, of course, only for an imprimitive group, because remember the connected components of a graph, they give you a system of imprimitivity. So if I have a primitive permutation group, then of course the Saxl graph is going to have to be connected, assuming there's an edge in there, which it will if the group has base of size 2. The next thing we looked at was then the diameter of your Saxl graph. And so we want to know, well, can I make my diameter arbitrarily large? And indeed we can, because there is a group G such that a Saxl graph is the Reef graph with 2d plus 1 parts of size p to the d. And so this has diameter d. Okay, so remember your reef graph, I've got all these parts, all of size p to the d. They're arranged in a cycle. Every vertex in one part is joined to all the vertices in the 2 parts either side of it in the cycle. Okay, so that's why it has diameter d. Okay, and so I get the, I can get an arbitrarily large diameter for my Saxl graph. Now again, a reef graph, its automorphism group is imprimitive. Okay, those parts give me a nice system of imprimitivity. Okay, and looking at what happens in a primitive case, we are quite happy to conjecture that if I have a finite primitive group with a base of size 2, then either my group is a Frobenius group, in which case the Saxl graph is complete, or the diameter is 2. Now, I think when we first started looking at this, we wouldn't have dared to dream to make such a conjecture. But I suppose the first thing you do when you want to study primitive groups, you run through the database of primitive groups in magma and up to degree 4095. And we're able to check that indeed it was true for all those primitive groups. We're able to look at all the base 2 actions of sporadics, and except for possibly 31 of them where the groups are too large to determine what the diameter of the Saxl graph is. But in all the cases where we could determine the diameter, we find that the diameter is 2. So we have sort of like lots of computational evidence that this conjecture does hold. I did want to mention though that if I weaken the hypothesis of being primitive slightly to being quasi-primitive, then I can get out to diameter 3. Okay, we have an example, I think it's M11 on, I've forgotten the number of points, but we have an imprimitive action of M11, which has diameter 3. I'm not sure if we have examples though where it's an unbounded diameter in the quasi-primitive case, right? So these reef graphs, they are not quasi-primitive, right? They've got a very intransitive normal subgroup. Okay, so remember, a group is quasi-primitive if every non-trivial normal subgroup is transitive. Okay, so we must, if this conjecture is true, we must really be using the property of being primitive, not quasi-primitive. Okay. We actually have an even stronger conjecture, which we claim that not only should it have diameter 2, but actually any 2 vertices should have a common neighbor. Okay, so if I have 2 vertices which are not adjacent, then for the graph to have diameter 2, they need to have a common neighbor. But even if they are adjacent, we think that there should be a 3rd vertex which is adjacent to both. Okay, so that's actually an even stronger conjecture which we're also willing to make. Okay, so again, that's verified in for all these small degree actions and these sporadics. Okay. So why are we willing to make this conjecture? Okay, so this is perhaps small evidence. What happens if we go to larger n? Well, let's look at some asymptotics. So there's this quantity Q of G2, which actually was well studied. I suppose Q of GC was introduced by Liebeck and Schlev in their original paper. But Q of G2 is just, I take the number of all pairs of points such that their stabiliser of both of them is non-trivial, and I divide by n squared. And so this is the probability that a random pair of elements is not a base. And you can show that this is just one take the valency of my Saxl graph divided by n. Now, if Q of G2 is less than 1 over t for some integer t, then you get that the valency is at least n times 1 take 1 over t. And so this then tells you that any t vertices will have a common neighbor. And so in particular, if you take t to be at least 2, the valency is at least n over 2, and so your graph is connected and it'll have diameter at most 2. Okay, because since the valency is at least n over 2, any 2 vertices must have a common neighbor, and so it will have diameter at most 2. And indeed, any edge will be contained in a clique of size t plus 1. So that is this parameter Q of G2. So you can go and try and work out what this parameter will be for certain groups G. And as long as it's less than a half, your Saxl graph will have diameter 2. Well, the first groups we then looked at is if I take the almost simple groups with Saxl AM and such that G alpha acts primitively on 1, 2, up to M. Okay, so these were shown by Gralnick, Saxl, and Burness to have a base of size 2. And any two vertices of the Saxl graph have a common neighbor. So this is our this is more than just looking at small degrees. Okay, this is a large family of base 2 groups where not just the conjecture about the diameter, but even the stronger conjecture holds. Okay, any two vertices have a common neighbor. So that's one piece of strong evidence we believe for our conjecture. So the second piece of strong evidence is actually, so this parameter Q of G2, I said this had been previously studied by various people and was often calculated when trying to show that certain groups had a base of size 2. And so, for example, Joanna Fawcett in her PhD thesis had a couple of results. If I have a primitive group of diagonal type with the group induced on factors being neither the alternating or the symmetric group, then there is a base of size 2, and this parameter goes to 0 as the order of my group goes to infinity. And similarly, if I have a twisted reef group where the group induced on factors is primitive, then again, it's a base of size 2, and this parameter Q of G2 is going to 0. So again, as long as my order of my group is large enough, this parameter Q of G2 is going to be less than a half, and so therefore any two vertices will have a common neighbor. Okay, so this result is not saying that all primitive groups of this sort satisfy the conjecture. They're just saying as long as your group is large enough, it will satisfy the conjecture. Right? So if my group is of one of these two types and it has large enough order, then any two vertices will have a common neighbor. Okay, and so in some sense, I suppose the conjecture is true asymptotically for these things. So it would be interesting, actually, I suppose, to work out for some of the smaller orders as to whether or not it does calculate it, does satisfy it. So that's in some sense, these examples are in some sense where the conjecture is obviously true, right? Because it turns out that a probability that two vertices do not form a base goes to 0. So the probability that two vertices do forms a base goes to 1. So you've got lots of you have lots of edges in the graph, and it will of course have diameter 2. And so you might think, well, is the conjecture only going to be satisfied for those groups? Well, actually, if we go back to one of our previous examples, if I take PGL2Q and I take the Saxl graph, then we saw before that this was our Johnson graph. Now, in this case, if I calculate my Q parameter, instead of it going to 0, it actually goes to 1 as the order of my group goes to infinity. Okay, so therefore, there's actually not many edges asymptotically in my graph. Okay, so probability that a random pair forms a base goes to 0 as the order of my group goes to infinity. But we know the diameter of the Johnson graph, it still has diameter 2. Okay, so in some sense, this is the conjecture is not going to be true for silly reasons, right? But even it seems that for Saxl graphs where the number of edges is sparse, right? The edges are sparse, conjecture is still holding. Okay, so that's some more evidence. Now, this is of course only one primitive action of PGL2Q. And recently, so it's on the arXiv, but hasn't been published yet, is that Huya Chen and Xiaofei Du. They have shown that if I have any primitive permutation group of base of size 2, and where the Saxl is PSL2Q, then again, the conjecture holds, right? So any two vertices of my Saxl graph are joined by an edge. Okay, so this is just one, okay, this is the action of PGL2Q where your point stabilizer is a dihedral group of order 2 times Q plus 1. But they then look at all the primitive actions. Okay, and when you have a base of size 2, then they're able to show that the conjecture does hold. Okay, so that's some more evidence. And I think from memory, looking at their proof, there's definitely one class of, so sometimes, again, you can calculate this Q of G2 parameter. Sometimes you show that it goes to 0, in which case the conjecture is trivially true. But there was one case where they actually had to do a lot of work because that Q of G2 parameter did not go to 0, and there was a lot of work involved, and they had to work out what the diameter actually was. There's one family of groups which we think would be a good test case for the conjecture. So this is where I take my group G to be my dihedral group of order 2p, and I take a Reith product with my symmetric group on p take 1 on 2 points. Then if I have this group acting in product action, so this is on p to the p take 1 on 2 points, this actually gives me in disguise an affine primitive permutation group. It does have a base of size 2, and our Q parameter goes to 1. Okay, so this is where, again, you actually have to calculate what the diameter of the graph will be. Now, computationally, we could check that for p at most 13, the diameter is 2, but at that point, then the computer gives up for the next prime. The next prime is what, 17? Okay, and then it becomes too hard to check just on the computer. But we sort of feel, again, this would be a very interesting test case for the conjecture, right? And especially if the conjecture holds this family of graphs, then we would be even more confident. Well, we're confident because we're willing to make it as a conjecture, but in some sense, we feel this would be a very good test case for it. Yeah, we did look at trying to prove it in general, but I think it's very, I don't know, calculating the diameter is very number theoretic and combinatorial, and it was a bit beyond what we're able to do. But we think that would be an interesting case to look at. Okay, so that's the diameter. I just wanted to finish by talking about a few other possible graph parameters. Okay, so I suppose the philosophy I want to say is that if you have your favorite graph parameter, then often it has a nice, interesting interpretation in the Saxl graph world. So one is the clique number of a graph. Okay, so that's the largest complete subgraph. Well, then in the Saxl graph, this would be the maximum size of a subset such that any pair of points in the subset is a base. Okay, so can we say things about the clique number of a graph? So that Q of G2 parameter, if that's less than 1 over t, then we would know that this is at least t. So that's would help in that setting. Your independence number, so these are the largest subset of vertices with no edge between them, and so this is the maximum size of a set such that no 2 points forms a base. So that's our independence number. The chromatic number now, so this would be the smallest number of parts in a partition such that no pair in the same part is a base. So that would be what the chromatic number of your Saxl graph would be. And also the total domination number. This would be the minimum size of a subset lambda, such that for every vertex, there is some vertex beta in lambda, such that alpha beta is a base. Okay, so again, that has the nice interpretation in terms of the base size. So none of these have really been looked at. I suppose the clique number has been looked at a little bit through the Q parameter, but the others haven't really been looked at yet, right? But we would invite you to choose your favorite graph theory parameter and look to see what the interpretation can be in the Saxl graph and study what to see what's possible. And on that note, I'd like to finish there. Thank you.
Thank you, Michael, for the talk. Well, it's time for questions, suggestions, comments. So please go ahead.
Michael, if I can ask about the original program of Jan Saxl,
Yes.
this is still on Go, is that correct?
Yes, that is still on going.
So your diameter question for these graphs, it's all happening within the context of the program, but you haven't yet.
The first you need to work out which graphs have diameter, have a base of size 2, and then you have to then work out what their diameters are.
So just to check that your conjecture is currently about a class of graphs which you don't know completely what's in there.
That's right. I suppose we don't know completely what's in that.
Is there an obvious class of primitive permutation groups that you could mention for which it's not known that the base size is 2?
Sorry, that's not known that the base size is 2.
Yeah.
Well, not even if you look at just almost simple groups, I don't think we fully yet know which ones are base size 2 and which ones are not. Tim does have a large unpublished manuscript which tries to do it for classical groups, but as far as I'm aware, that's not finished. Exceptional groups, have I got the list for exceptional groups? I don't think so. They're getting there, they're narrowing it in.
Is it known for all the sporadics now, or is that the trouble that you run into computational issues with them?
Sporadic groups, I think they know exactly which ones have a base of size 2, except possibly 1 or 2 actions, I think. They got very close there computationally. Yeah. There has been some work recently with affine groups, like Melissa Lee, that was her whole PhD thesis. It was looking at base sizes for when you have a C9 subgroup acting irreducibly on the vector space. Trying to work out when they're of base size 2.
Okay.
I'm not aware of anyone, say, doing, say, calculating exactly. Oh no, Joanna's stuff for diagonal and twisted reef. So for the twisted reef, where it's primitive on factors, you know it's base of size 2, but when it's imprimitive on factors, I don't think anything's known, for example.
So even for twisted reef, it could be something like, depending on what the group is on the factors, sometimes it will fall into being base size 2 and sometimes it falls out.
Possibly. I'm not sure if I know an example where it's not a base size 2. Let me go back to the.
Very tricky.
Yeah, so if the group induced on factors is primitive, then you know it's a base size 2. I'm not sure if she has an example where it's imprimitive and the base is not of size 2. I'd have to look. She never actually wrote this up and published it. That's all just in her thesis.
Can I just ask one quick question as well? So about the twisted reef groups then of that are quasi-primitive but not primitive, is anything known about their base size, even if you have some conditions on those?
On the twisted reef case?
Yeah, just for primitive, for quasi-primitive.
Deeply into Joanna's thesis.
Okay. Thank you.
Okay. Any other question? Okay, if Nino, you?
Sorry?
Did you wanted to ask a question or?
I don't have any questions at the moment.
Okay. Well, Michael, thanks once again. Have a nice time in Australia. Hope the situation will be better soon, so we could travel a little bit more than we are able now. So
Yes, that's right.
hope
Yes.
you-
When I'll next be able to come to Slovenia.
Are you actually able to leave Australia at the moment?
Oh, actually, no. Actually, I don't think the government would let me at the moment. Yes, I think Australian citizens are banned from leaving overseas. They need to apply for permission.
Is attending a conference valid permission or not? A valid reason?
Well, not for a normal person like me. I think if you're a politician, then yes. But perhaps I shouldn't say too much. This is being recorded.
Oh.
Yeah.
You have, if you want to leave the country, you have to apply for an exemption, and you'd have to have a good reason. And in the same way that if you're not an Australian citizen, you need to apply for an exemption to come in.